Let's go ahead and talk about Lewis structures. So Lewis structures are diagrams that help us understand how chemicals react and behave. And they're actually little fun drawings that help us, again, picture what the molecules actually look like. Well, you should already know going into this. You should know about valence electrons, how to determine them on the periodic table. Also, you should know the octet rule. You should understand covalent ionic bonding, and also, to a certain degree, some Lewis dot diagrams. By the end of this, you should be able to draw Lewis structures, especially for covalent molecules and ionic compounds as well. So again, why do we do this? Well, again, just to make sure that there's some history behind this. It's really an application of those Lewis dot diagrams from a long time ago, and they're also helpful in identifying properties of chemicals. They can also help us explain and anticipate certain behaviors just by looking at a structure. You'll be able to predict how it's going to behave in certain contexts and things like states of matter. Is it going to be solid, liquid, or gas, or what do you need to make it boil and that kind of thing. Also, it's useful mostly for covalent molecules, as mentioned before. Now, we're going to talk about an advanced method. There is a simple method of this, but I just want to go ahead and get an advanced method because it seems to be much more universally applicable. There are a couple steps you have to know. This one, again, it will help us address multiple bonds, something called coordinate covalent bonds, and then also expanded octets, all of which are terms that you should at least be familiar with. A few terms that you have to know. First of all, this one right here, a pair of electrons shared between two atoms. Hopefully you recognize that as being a single covalent bond, right? Just one pair, and then it is shared, so it's a single covalent bond. The next one, a pair of electrons not involved in bonding. There are several terms you can use for this, but the one that I'll probably use most often is lone pair. So lone pair, L-O-N-E, meaning, again, not with anything else. So two electrons that are by themselves. Another alternative to this phrasing might be non-bonding pair of electrons. So again, either lone pair or non-bonding pair of electrons. This next one, two bonding pairs between two atoms. Well, if a single pair between two atoms is a single bond, then two bonding pairs must be a double bond. The last one here, three bonding pairs would be called a triple bond. All right, now I'm going to go through a series of steps, and you must follow these steps in order to be 100% successful. First of all, find the total number of valence electrons for all atoms involved. You must find the total number of valence electrons. Next one, arrange the elements so that the least electronegative element is in the center. So you definitely have to know your trends in electronegativity to be able to be successful at these as well. One exception that you should go ahead and note is that hydrogen is always on the outside and never in the center of your structures. So anytime you see hydrogens, go and expect it to never be in the middle. Use some other element. Number 3, draw one covalent bond between the center atom and each of the outer atoms. One single bond. Do not try to add double bonds. Don't try to do any funny business. All you're doing is, again, connecting the central to all the outer. Don't connect the outers to each other. Each covalent bond, you should know this by now, also represents two electrons, because, again, it's a pair of electrons. And then at that point, you want to also determine the number of remaining electrons. So out of all the valence electrons that you had to begin with, after you've designated a few as single bonds, how many remain to be assigned? Step number 4, add any remaining electrons to the outer atoms as lone pairs to satisfy the octet rule. Remember, these are pairs, so you should never put them as individual electrons or try to separate them anywhere else. Make sure they also don't end up looking like another covalent bond where you put it between two atoms. They should be assigned just to the central atom, and they should be completely independent of any other atom. And at this point, again, determine how many electrons you have. And step number 5, add remaining electrons to the center atom to satisfy the octet rule. If, at this point, the central atom still does not have an octet, it does not have the full 8 of the electrons around it, then you will use lone pairs on the outer atoms to form double and triple bonds. One thing I want to mention, you always have to keep adding electrons until you run out. So if you run out of electrons at step 3, then you don't have any more electrons to keep going. You don't have to worry about step 4 or 5. Same thing goes for rule 4. If you run out of electrons at step number 4, then you don't have to keep going on to step number 5. Also, every single time you do a Lewis structure, always go back and double check the octet rule. Make sure that each atom has satisfied the octet, or else you will not get the correct structures. Let's try some examples. Now, you should have the rules already written out in front of you, so I'll refer to them every so often, but make sure you're following along as we go through each example. Let's start off with CH4. CH4, by the way, which is methane. If you look at the structure, again, you would go ahead and count out the total number of valence electrons. By looking at its location on the periodic table, carbon will have 4 valence electrons. Hydrogen will have also 4. Individually, each hydrogen has 1, but since there's 4 of them, you'll contribute a total of 4. So that means your total number of valence electrons that you have to assign is going to be 8. That's step number 1. Step number 2, arrange them so that the least electronegative element is in the center. Well, as it turns out, since carbon and hydrogen are the only elements, hydrogen can't be in the center, so without having to really look at the electronegativities, carbon will have to be in the center. So let's go ahead and arrange it so it's in the middle and hydrogens are around it. As I write these out, just note that you don't have to make hydrogens again in any particular order. It doesn't really matter where they are. Visually, though, it's nice to have it symmetric or make it look like it's a reasonably kind of a reasonable molecule. But of course, that comes with some practice. Step number 3, go ahead and draw a single covalent bond between the central atom and all of the outer atoms. Remember, I'm not connecting any of these. So do not try to connect any outer atoms to each other, only to the center atom. Once you've done this, go ahead and count out how many remaining electrons you have. Since each bond has 2 electrons in them, right now I have assigned 8 electrons as of this moment. So how many electrons then remain? I started with 8. I've now assigned 8. Therefore, I have 0 electrons left. So at this point, I can stop assigning electrons, and step number 3 will be my last step. Go ahead and look at the last part then, of course. Once you're done assigning electrons, go ahead and check the octet rule. Carbon right now is in the middle with 4 bonds, and again, since each bond has 8 electrons, or 2 electrons, you have a total of 8 around the carbon, and again, these bonds belong to the carbon as well as the hydrogen. So these again technically belong to the carbon, so these also do so. Total of 8 electrons around the carbon. That satisfies the octet rule. Now, hydrogen, however, is a little bit different. If you look at hydrogen, well, it only has this, for example, only has 2 electrons that belong to this hydrogen right here. Well, that's not really an octet rule, right? Because that's, well short of the 8 necessary to satisfy that rule. But hydrogen is an example of one of those exceptions. Hydrogen is perfectly satisfied with only 2. Right? It cannot take on any more electrons. Taking on 2 electrons gives it the noble gas configuration, which looks like helium, which gives it a stability that is perfectly satisfying its own energetics. So at this point, this structure is perfectly fine the way it is. So that is the complete Lewis structure for CH4. NH3, let's go and run through this example. Nitrogen has 5 valence electrons. Hydrogen individually has 1, but there are 3 of them, so you should have a total of 3 electrons. And that then gives you a grand total of 8 electrons that you have to assign. Step number 2, arrange it so that the least electronegative element is in the center, unless it's hydrogen, in which case it always goes on the outside. So in this case, nitrogen has no choice but to be in the middle. So nitrogen, and then hydrogen, hydrogen, hydrogen around it. I was a little premature and started drawing in my bonds, but I can already know that it's going to be there. So step number 3 is already taken care of as well. Hydrogen, again, with nitrogen, each of these will have single covalent bonds. And at this point, let's go ahead and count out how many we've used up. So after step 3, after I've connected all of the bonds, you should know that there are 6 used up, so only 2 electrons are left to assign. So then we move on to step number 4. Step number 4 says, assign any electrons left to your outer atoms until they have the electrons satisfied, until the atoms satisfy their octet rule. Well, hydrogen, again, right now only has 2 electrons associated with it as an outer atom. But again, its octet rule is satisfied, so we don't have any more room to put any more electrons on any of these hydrogens, because with just 2 electrons, they are satisfied. With that, then you have only 2 electrons left, so step number 4 is done. Step number 5 says add any remaining hydrogen electrons then to your central atom, which is nitrogen. So then I'll go ahead and do that as a lone pair there. At this point, go ahead and double check that you have used up all the electrons. Again, I have 6 used up here, 2 more right here, and that gives a total of 8, which means that we've used all of our electrons. Now, we're not quite done yet. As always, we check the octet rule. Hydrogens, as we said earlier, they're all good because they have the 2, but nitrogen, they have 2, 4, 6, and then the 8 around it as well, and that is satisfying the octet rule. So this is the correct formula for ammonia, correct structure for ammonia. Let's take a look at another 2. H2O, this one right here, again, the same deal. Go ahead and start with step number 1. 2 electrons, 6 electrons, for a total of 8 electrons. The next step, go ahead and put the least electronegative in the center. Oxygen will have to be in the middle here, even though it's not the least electronegative, excuse me. Even though it's not the least electronegative, we have no choice but to put it there. And then let's go ahead and arrange this so the hydrogens on either side. Step number 3, go ahead and draw a single bond, which I kind of already did accidentally, but go and draw a single bond between each of your outer atoms to the central atom. And then let's start figuring out how many we have left. We've used up 2, 4 electrons, so we have 4 remaining. Those 4 are now going to be placed on our outer atoms on step number 4. So step number 4, again, try to put them on the outer atoms, but again, since these are already satisfied with the octet rule, we will not put any more on the hydrogens. So that step 4 is completed. Step number 5, place them on any remaining electrons on the central atom. So let's go ahead and do so here. All right, there you go. So that is all of our electrons assigned, and we have no more left to do. Looking at the structure here, you should have 2, 4, 6, 8 electrons assigned to your oxygen here in the center, and that has the octet rule satisfied. Hydrogen also has its octet rule satisfied, so everything is satisfied. The structure is complete. Let's try this last one, CH2O, also known as formaldehyde. Carbon has 4, hydrogen has 2, oxygen has 6. So 4 plus 2 plus 6 gives you a grand total of 12 electrons that we need to assign in our structure. Let's go and start arranging it according to our step number 2. Let's put carbon in, well, actually looking at the possibilities here. Hydrogen, of course, cannot be in the center. So you're left to compare carbon and oxygen to see which one will be placed in the middle. Remember that it's the least electronegative, so by looking at the trends, you should recognize that carbon is the lesser of the electronegative elements. So carbon goes in the center, and let's go and put the rest of them as outer atoms around the central atom. Step number 3, let's go ahead and connect them all with a single covalent bond. So connect those, and then count how many electrons we have left remaining. There are currently 6 electrons that we've assigned here, and 12 to begin with, so that means then we have a total of 6 remaining that we have left to assign. So 6 electrons left to assign. That's step number 3. Step number 4, let's go ahead and move on to this one. We will now try to assign any electrons to our outer atoms. As we saw before, hydrogen with a single bond has satisfied its octet rule, so there's no need to add any electrons to hydrogen. So the only other alternative is to add electrons to our other outer atom, oxygen. Now, right now, we have to only have 2 electrons associated with our oxygen, so then we have to keep adding electrons until it satisfies the octet rule. At this point, we've added 6 more electrons. Those 6 electrons help complete the octet for the oxygen. Therefore, we are done adding electrons to our oxygen because there's no more outer atoms. Also, concurrently, you notice that if you look at the number of electrons remaining, there's no more electrons remaining, so then we are good there. All 12 electrons now are assigned to our structure. Okay, so then we are done, right? Well, don't forget, every time you assign electrons, you always have to double check the octet rule. So once you're finished, you have to go back and check the octet rule for all atoms. Hydrogen, as we saw earlier, is good. Oxygen, as we just made into a full octet, is also okay. But our carbon is actually deficient in electrons. You only have 2, 4, 6 electrons here on the carbon. So what do we have to do? We have to take some of these outer atoms, according to step number 5, we look at the outer atoms and then bring a pair of electrons into the middle so that they can be shared by the carbon and the oxygen. So these will be brought in here, and the resulting structure will look like this. You have a double bond, and the carbon-oxygen bond is perfectly fine. So you have 8 around the oxygen, 2, 4, 6, 8 electrons, and now the carbon is also satisfied. 2, 4, 6, 8 electrons. So anytime you're deficient in the center, go ahead and try and double bond from one of the outer atoms of your outer, lone pairs from one of your outer atoms. Right? This is the only step in which you are allowed to start using double bonds. Some exceptions you have to know. Some of these right here need only 8 electrons, or need less than 8 electrons. Hydrogen only needs 2, as we saw earlier. Lithium only needs 2. Beryllium needs 4. Boron needs 6. And also you should recognize that there's an expanded octet where any p block elements in period 3 and greater, so period 4, 5, 6, remember p block is the right 6 columns. These empty d orbitals may engage in bonding and allows for something called an expanded octet, where up to 12 electrons can surround the central atom. It's not required. Let's try some examples here. You can pause and try these out on your own first. And here are your answers for these.